So we will take a more formal approach today based on, let's see, what we discussed last week. So let's start with, so you recall normal form games? We will be using this for the foreseeable future. So you may, just to recall, do you remember what are the ingredients of the normal form game? You have a set of players. You have a set of action sets for each of the players. Let's call it for each of the players. You have this. And what else do you have? You also have a, sorry? Yes, utility function. So the utility function is defined over the product space of the action space. And it's a real value. It could actually be half. It could have negative utility. Right? Okay. So I have to use, like in any subject you learn, we'll standardize some notations and we'll sort of keep on using them, okay? And some of them are of particular significance because we'll keep using them. So I'm going to give some names, okay? Let's start by this object. Okay. So it's nothing but all of you, at least this, right? This. So we call every element is called the action profile. It's basically a vector of actions, right? It's a vector of actions for where each coordinate represents the action of that individual player. So each element of this A is an action profile. So sometimes in some books, they'll call this action profile space or action space. But that's not really that standard. Okay. So the utility functions of each of the agents are actually defined from this as a domain to the real line, right? Okay. So now, so a strategy, let's call it a pure strategy, of player I is basically an action from his action space. So in general, different players can have entirely different action space. This is why we index it with I. The examples we saw last week, it wasn't quite that, but this is in full generality. So we'll generalize this to this thing called mixed strategy. Okay, so if we call this a pure strategy, every element of this action space is called a pure strategy profile, okay? I mean, so when I say pure action profile or pure strategy profile, they mean the same thing. Can we reduce the volume a little bit? Like, so that I hear my voice a little less. Is this my microphone, maybe? Okay, let's continue. I'll just get used to this probably. Fix this. Are you all seeing something? Okay. So what's a mixed strategy profile? What's a mixed strategy? It's basically a probability distribution over that individual to the player's action space. Okay. So we denote it as a vector like this. Let's call it xi. So I'm going to try to be very consistent by whenever I talk about a pure strategy, I'll use an A. And when I use a mixed strategy profile, mixed strategy, I will use xi. Okay. So just if you're confused, please ask. Okay. So xi is basically defined over this set. You may have seen this in this is a name for it. Okay. So what I'm doing is I'm representing the probability distribution as a vector, and the vector is indexed. How long is the vector? It depends entirely on how large the action space is, and the just that x when projected onto the coordinate indexed by a, all of them must sum up to 1. So this is sometimes called, I think oftentimes called the probability simplex or standard simplex. So it's a um, it's a subset of this direct product of reals. Now, okay, so mixed strategy profile is such a vector of distributions delta I. Okay, and this also we will use a short form. We call this the delta. Okay. Okay. Any questions so far? Okay, these were all just definitions. So, okay. So now you recall that the utility function is defined entirely on the action space. But what the reason we have introduced this is to basically capture the fact that sometimes players, so there's a lot of discussion on what mixed strategy actually represents. Does it really represent the behavior of one player, or does it represent the behavior, expected behavior of players who are rational, but they don't know what the others are doing, and therefore they are sort of mixing their actions, the course of action they take. Okay, so and there are a lot of interpretations, and people have done sort of serious research work even on that. Okay, so that's, I think, studied formally under behavioral game theory and so on. So, but what we are going to do is, so if we believe that, okay, sometimes players be sort of use mixed strategies while playing a game, so then there should be a natural notion of what their payoff is when they are using a mixed strategy, right? So that's what so the expected payoff okay using I using X is defined as follows. Now, I said this last week and I didn't repeat it, so it bears repeating. As of now, we are assuming players are rational, meaning they're trying to, we don't rational and acting independently. Okay. So, I just unravel this, let's say, X hat. So X hat is a mixed strategy profile. Okay. So it is of this form. So now we know that player I's payoff does depend on what the actions other people are taking. So the point is how to then extract the expected payoff for player I, given that everybody is now using sort of a randomized strategy. Okay. So we define this as follows. So each xi, the intuition for this is the following. Each xi is what? It's a mix. It's a distribution over their individual actions, right? So we basically think of x being, let's say, what am I using? Yeah, this. Okay, notationally, let me write it this way. It's going to be, okay, let's say. I'll explain what I mean by this. Can't really write it. Ui of A, which is. So we will use the shorthand to mean this, okay? This is a bit of an abuse of notation. UI was defined on the action profile. This is the quantity I'm trying to compute, which is X bar is the profile of all the players. Each player has picked his mixed strategy from his probability, from its mixed strategy space. And in doing so, what is he actually doing? If you think about all possible actions that he can undertake, he's basically, all of them taken together, you can think of it as being split over this action profile or this action profile or this action profile and so on, right? So basically what I'm trying to do an expectation computation over is what is the probability that this action profile has been sampled from the action space and the probability that is realized. I'm going to write it as realized, okay? In actually by, let's say, times this would be the definition of expectation used on this. Okay. Now the question is, how do I compute this? Now we use the fact that players are acting independently, right? So basically, if action profile A has to be realized by X bar, what we do is, it's visible, right, from there. X. Okay, I'm not going to use I anymore because this X P of AP. So A bar is, remember, of this kind. A1, action. This is how we are notation, right? So the pth player plays action AP with what probability for his distribution X? This is what this quantity is. This times this value. Okay. Is it clear? This is what we define as, it's both a definition. I mean, obviously it's a definition. Expected payoff. I think, okay, I've written there already. Okay. But I hope you understand why this seems to be a logical, given that our utility function is defined over the problem, over the action space, and players are playing independently, right? So to generate what the expected payoff should be when a mixed strategy is played, the entire sample space basically splits over each possible realizable profile, right? And once you have that mental picture of the probability space, then you can just simply apply a definition of expectation. Okay, so now using this, we talked about dominant strategy last week, right? And I said the dominant strategy of a game, a player may have a dominant strategy when there is clearly an action he can take that gives him as good a payoff as if he were to compare, it gives it as good a payoff no matter what the others are doing, right? So we will sort of formalize that in terms of mixed strategies also. So, okay, any suggestion as to how we can do that? Hold on. Okay, let's say, so, okay, we can, okay, strategy. I'm going to write MS, okay? It's just easier that way. XI. Let's call it weakly dominates. We can analogously define what strongly means. If, yes, tell me now. UI hat of XI X minus I. Okay. Greater than equal to Hmm. X. Okay. Sorry, say that again. Okay, so we are saying Xi weakly dominates Xi prime. Okay. If what happens? The expected utility when individual I is playing strategy Xi, right? And so what does X minus I actually represent? Okay, so this, okay, so this is, you're saying is the expected payoff. Let's write in words, okay? For I, when the entire profile, when people are basically, all the players are playing this profile, right? He's playing Xi and others are, so it's not clear to me what X minus I is, because Xi is just a mixed strategy for the player I. Usually, when we write this notation, X minus something, we are basically talking about a profile. Like, you know what, there is an understanding that this X bar contains the mixed strategies of all the players, of which you're dropping the strategy of the ith player, and all others continue to play the same. That's what this represents. Okay. There is no X minus I here, has no sort of semantic meaning. But you're sort of right. What should this be? So just think in terms of what did we say? Dominant strategy is something where we want to say that Xi is gives you player I at least as much payoff as any other strategy employed by the other players. So this thing, as long as I can make this to be, let's say, just to avoid confusion, right? So let's say for all, this is basically a strategy profile of all the players without I, yeah, with I being missing, right? So basically, this is what it, no matter what others are doing, playing Xi gives him at least as good a payoff as playing any other strategy I prime. here. In fact, right? Do you understand? So we are just comparing xi versus x prime I, no matter what that y minus I is. So you guys came in a little late. I hope this is fine. Okay, so let's just, so I'll keep this definition on this board, at least for this today's class, because this is sort of new. Okay. Okay, so I'm not going to write, but you know what this means, okay? All right, so, okay, is there something else? Okay, so what would be strongly? Strongly basically just means this becomes tricky, okay? Nothing more. Okay, so can you tell me what dominant strategy equilibrium should be? Again, it's a term we saw last week. So dominance, so equilibrium is at the very least a profile, okay? Just one person playing a strategy does not make equilibrium. Equilibrium is a state attained by all the players together. So always remember that. So for that to make sense, we always have to talk about a profile, which is basically a vector of strategies for all the players. So that's one thing. So X bar is dominant strategy equilibrium if what? If I can't hear, I think. Okay, that unilateral deviation is for Nash equilibrium. Yes. So basically, there's a one step of this missing. If among all the strategies that player I can, you can hear me, right? People, you guys can hear me too? People who are attending over Zoom?
Yeah.
Yeah. Yes, ma'am.
They can, right? Okay, then I can just keep the mic low. Otherwise, sort of. Okay. So the point is that this is just a dominance is from the perspective of one player. Now imagine a mixed strategy profile where every player has a dominant strategy and they're playing that dominant strategy. That's basically the vector we are talking about. Okay. Now they can be more than one dominant strategy. In that case, you pick one and so on. The main point is that if this property holds for the strategy space of a player I, okay, that is when a dominant strategy equilibrium makes sense because everybody actually has to play their dominant strategy. So a dominant strategy, let's just maybe write a intermediate definition first. Dominant strategy for player I is some xi that, let's say, weakly dominates all okay. Weakly because you can have multiple dominant strategies also. Okay. So a dominant strategy equilibrium is basically a vector such that dominant strategy I. Okay. Okay. This, when I write this and I am writing this, it means I'm talking about this vector. Okay. All right. So Now, okay, now let's go to the, so if you remember the examples from last week, there were games in which a dominant strategy did not exist. Okay, let's talk about a game. Confession or cooperation, that thing is the dominant strategy for each of the prisoner, for each of the convicts, or okay, prisoners maybe. But tell me an example of a game where there was no dominant strategy. Sorry?
Matching
Okay,
points.
the left, right, you're talking about the traffic game. Okay, matching pennies. Why? Yeah, so the idea was that you start from any position. Those were small games, so we could just sort of analyze it brute force, right? You start with one thing and you see that, well, if my opponent was doing something else, right? How did my payoff change, right? Did this for the role player, did it give him as good a payoff as this entry? This entry corresponds to a situation where the role player continues to play this, right? The player who is continues to play the same thing, but this column player has shifted, right? So then, so that sort of thing, yeah. And this would be, well, the column player makes the determination, well, even if the role player shifts, this still gives me the best possible outcome, right? So when that sort of thing happens, that's when we have a dominant strategy. And all those matching pennies and those left, right thing, this was not the case, right? Okay, so this is what it means. I am here, this strategy, playing this action for this role player, gives it at least as good a payoff as no matter what the other guy does. So what the other guy can do, it can continue to play this thing or it can move to something else, right? So similarly, and you analyze for all four of this and see that, okay, such a self does not exist, such a state does not exist, okay? All right. So there are examples where dominant strategy does not exist. Now, dominance, why do we even care about dominant strategies? Do you hasten to take a guess? Yes, it at least makes game analysis rather straightforward, right? Because the issue of whether in an arbitrary game, players can reach an equilibrium and all, that's a very complex question that requires people understanding other people's strategy space, the payoffs, and how, and so on. And there can be very complicated there can be very complicated factors that affect how these are very small games, and you can sort of easily sort of do a sort of exhaustive search and so on. The moment you have many more players, the whole situation becomes very complex, right? So, but the dominant strategy is basically saying that in a sort of very myopic way, people can rationalize about their outcome. Now, it absolutely does not imply that this is the best thing they should do, because among all possible strategies all of them can employ, this is going to give them the best payoff. That's not what it says. Because in that prisoner's dilemma game, again, not confessing, right? Both of them not confessing, or rather denying, would have given them the best payoff, right? Because that was the outcome there. But at least because each player has no control over what the other would do, existence of a dominant strategy allows them to argue about their payoff in a very straightforward, greedy way. That's the whole point. But it turns out dominant strategies are rather hard to find in sort of they don't exist for the, for the most part. It's kind of a rarity when they do exist. So I just say this, that in next few weeks, we will see, not just the coming weeks, but further along in the course, we will see that when we try to design games, okay, that's one aspect of game theory, which is mechanism design. We actually try to design games where there will be dominant strategies. That's one of the imperatives of game design, because we want people to be able to think about the game in a very sort of proper way, rationalize it, and the game design will ensure that if everybody played the dominant strategy, a desirable common outcome will be attained. Okay, so that we will see later on. So in the absence of dominant strategy equilibrium, we talk about this thing called Nash equilibrium, okay, named after John Forbes. Nash. This is what Dipro was saying. So X, again, a profile, is Nash equilibrium if there does not exist any player with unilateral deviation. I'll explain what this is. Strategy. It's easy. Strategy. Okay. Let's say we'll call it UDS. So what is a unilateral deviation strategy? It means that, so a unilateral deviation strategy would be some X prime I from the mixed strategy space of player I such that the expected utility when player I deviates to playing X prime I, okay, but all the other players continue to play whatever strategy they were playing in that profile, okay, is greater than, strictly greater than, basically, let's say, if I break it down, so player I was playing Xi anyways in this strategy, right? So this is basically the same thing as saying Ui bar, X bar. Okay? This. So unilateral deviation is something, so such a strategy needs to exist. It's not that I want something more payoff, but that there is a strategy I can employ while all others are remaining the same. That's the significant difference between dominant strategy. Dominant strategy was against all strategies of other players. Here, the players continue to play the same old strategy. Okay? All right. So, can you tell me of an obvious relationship between the two? Is one the other? Yes, a dominant strategy is obviously a Nash equilibrium, right? Yeah, because it's arguing against everything, in particular when the other players don't deviate. Okay, good. So now, so when this strategy profile is pure, meaning they're not using mixed distribution, all the players are playing actions, right? That's what it's called, a pure strategy Nash equilibrium, okay? Pure Nash equilibrium is when X hat is basically, so you can think of it, this also as a probability distribution where all the probability mass is dumped over this action and everything else is zero, right? All right. So this says that no, so Nash equilibrium is one where no such strategy exists for any player, okay? All right. So that brings us to this very celebrated result that remarkably short, but it really launched, sort of proverbially saying, 1,000 ships. But before we get to it, let's talk a little bit more about some properties of the mixed strategy Nash equilibrium, because we will be using it. Okay. So, okay, let me. So the deviation strategy in the definition of Nash equilibria, it talks about another mixed strategy, right? Nowhere are we asking the deviation strategy to be a pure strategy. There may be a pure strategy where I just opt to play some action and I get a strictly better outcome. That may happen. or it may not be so. And the only way I can get a strictly better outcome is if I opt to a mixed strategy. Okay, that's what this allows us. Okay, it turns out that if such a unilateral deviation strategy exists, then there's also an action, unilateral deviating action, meaning they will, if such a mixed strategy exists that gives me a strictly better payoff, then there is some action I can take, okay, and that action belongs to the support of. Okay, so let me, so I guess you guys heard the definition of Nash equilibrium, right? So I'm going to use, okay, so the point is that usually working with probabilistic objects, unless we have very clear interpretation of what that is, can be a bit tricky. So oftentimes, one way to do it is to sort of massage the definition and see that if it can be reduced to an equivalent definition that strips away or at least minimizes the use of the, the randomization and mixing and so on and so forth. Okay, so this is basically one of those things. And this result and the implications that follow from it become very handy when working with Nash equilibrium or generally mixed strategies. Okay, so what this is saying is that if you have a mixed strategy X bar, this is a mixed strategy profile, it is a Nash equilibrium if and only if for all players and any two actions for that players, AI and AI prime, as long as one of them is in the support of this Xi. So from this mixed strategy profile, you extract the mixed strategy used by the player I, okay? The two actions that I'm basically going to compare, one of them has non-zero mass under that mixed strategy. That's what this means. This condition is called AI. Action AI is in the support of Xi, okay? Then we can say that the utility, okay, expected utility obtained by player I by just shifting to this, deviating to this action AI, okay, is at least as good as if it shifted to any other action. Okay, so notice one thing, if A prime I is also in the support of Xi, then you will basically get the same utility, right? Okay, this is also, sorry, that's just a mist. Bidirectional, meaning, yeah, so if A prime I is also in the support, A prime I can switch places and I could apply the same thing. Then basically what we would, this is at least greater than this and so on, right? So what we are saying is it's strictly less for all those actions that are outside the support. Nay, all actions. Okay. So, okay. So a mixed, this is for all I and let's say all actions. Okay. So what we want is all pairs of actions, let's say, but as long as one of them is in the support. Okay. Okay. Yeah, these are subtle points. So yes, please do pay attention and ask. Okay. So this is what this is. Yes. Yes, it would give me the same expected payoff if, I mean, that player I is the only one switching and others remain the same. Yes. Okay. Good. Hold that thought. Okay. So others, I'll just use that sort of observation to sort of infer something else that would be actually useful for us. So this is clear what we mean. This sort of thing allows us to say that if a mixed strategy is Nash equilibrium, we can say something very meaningful about the actions that are in that strategy support. Okay, all right. So now tell me, if X is not a Nash equilibria, then what does that mean? Wait, okay. So this lemma, okay, I'm not going to prove this here. This will be part of our homework, okay? So you will prove this lemma using, I'll add this to the first homework. You will prove this lemma using this definition, Nash equilibrium and unilateral deviation, okay? All right. So the consequences of this is what? Tell me. Tell me a bit formally so that we can use it precisely. So if X, you assume this to be true. If X is not a Nash equilibrium, there should be some pair, AI and AI prime. One of them is in the support, right? And the other one I don't know, right? One of them is in the support. And then this thing reverses. It becomes strictly. The thing that is not in this becomes strictly more than this, right? The one that is in the support. Okay. So then, what would that A prime I be? It's satisfy this condition that it's a deviating action that gives him a strictly better payoff. Correct? So I can say that if X is not a Nash equilibrium, there exists AI prime such that all these are expected, okay? There exists an AI prime okay, let me not write this. Is this clear? Yes. As a contradiction of this, as a contrapositive of this statement, if X is a Nash equilibrium, there exists no pure strategy or no action that this individual can take that will give him a strictly better payoff than any of the action within that support. Yes, yes, that's why. Okay. Okay. This is what, whenever we argue about something not being a Nash equilibrium, this is the property that we use. Because then it becomes very easy for us to say. It says, okay, if this is not a Nash equilibrium, there is a pure strategy which he can play that gives him a strictly better outcome. Okay. See, I'm not saying that this constitutes a Nash equilibria or that this gives him the maximum payoff among all other strategies, and none of this. Just that it witnesses a positive deviation, positive gain. Okay. So I think Sanjay is there. So I'll leave this reserved for homework. Okay. This lemma. Okay. And use this definition. Okay. So, all right. So now, okay. Now, just a bit of a, I should say here, because it's an algorithmic game theory course. There, right after, I'll show this. So you can have a situation where the Nash equilibrium, okay, all these values that are emerging of a Nash equilibrium are all irrational. We don't know as computer scientists how to handle irrationals. Okay, but Nash equilibria is a very important concept and we should want to be able to compute it and so on and so forth. So therefore, there's a notion of epsilon approximate Nash equilibria. So what we want to say is this is a Nash equilibria. We want to get arbitrary close to it. Okay, so that is the idea of a I am running slightly short of time. So I'm going to write here that we have these notions, and I'm going to get to them when we need it, okay? So there's an approximate. There are a few different notion of approx. Epsilon Nash equilibria. They epsilon well-supported Nash equilibria and so on. Okay, so we'll get to them. I'll define them when we need it. So let's call it lemma 1. Before I get to the main theorem of Nash, let's just stare at this for a little bit, okay? And see, so you agree here that this expectation, this UI hat object, is linear on what? It's linear on the action profile, correct? I can sort of analyze this further and show that it is actually linear over the actions of the player I. Okay, so UI, this is how I'm defining. Okay, yeah, it's okay. If I need more indices, we'll see. XI, AI times. What do you? Yes, tell me. Should I use this? Okay. Sorry. I was going to say something that I forgot. Okay, sorry. Okay. Okay. So it's the same UI X bar, UI hat, but now written this way. So what actually is this saying? And let's compare that. I sort of said it verbally, but still let's look at it a little bit. Okay, yes. So basically, this quantity is obtained by just looking at the X, this X bar vector, looking at the individual probability distribution, X1, X blah. Action, what is its probability mass, right? So some of the actions which are not even in this, in its support, they will contribute 0 here and the entire term will vanish, right? So this is basically summation about over all the supported actions of the XI mixed strategy, correct? Okay. So what basically we did here, it's, if you'll see, we are trying to use, we started with what seemed like a common sense definition and sort of simplified it, sort of analyzed, used this utility function. Okay, why this is the way we define utility function? That's the theory of economics, comes from utility theory and so on. We don't discuss all those things in an AGT course, but this is the way it is. And we extracted sort of a reasonable definition, mathematically correct definition of what an expected payoff should be. And from there, we already noticed this is linear over utility defined over the action profile, right? Here, we are burrowing down further and saying that this is basically linear over this sort of an action profile, this sort of a strategy profile, where here, this person is using a pure action, and these other players are using their, the previous, this XI action. Sorry, the action that the mixed strategy they were using in this vector X. Okay, so I'm going to try to prove this. Let's for now come and, but let's just assume this, prove Nash's theorem, and then I'll come back and maybe use that side of the board and prove this, okay? Nash's theorem. In every finite game, when we say finite, we always mean where the action space is finite and the number of players are finite. For the number of players are finite, and for each player, that AI set is finite. Okay, so that's a finite game. Every finite game has a mixed strategy Nash equilibrium. Can you think of a finite game where, so notice I'm talking about mixed strategy here, okay? I'm not claiming this about pure strategy. So from the examples that you've seen, can you tell me of a game where a pure strategy Nash equilibria does not exist? Acha, matching pennies. Okay, why? Mm-hmm. 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 Just by shifting. Okay, yeah. Okay, so I should mention, so I said that matching penny is inherently sort of the background action is random. You're flipping a coin. There is a deterministic simulation of the game, and Sanjay pointed out, it's like you decide what the coin, what head or tail it is. You don't reveal it, and it's a simultaneous reveal thing. Okay, it's the way I said matching pennies, it could have been sequential and so on, but here, if you think of it as a simultaneous reveal thing, you don't need randomness. Yeah, okay, so that's a game where you don't have a pure strategy Nash equilibrium. So again, existence of pure strategy Nash equilibrium is actually kind of a rarity. Very specialized games have it. We will look at them later on in the course. It's called the potential games and so on. So all this talks about is that of mixed strategy Nash equilibrium. Okay. So, so how do we prove it? Okay. So proof of this is for any player, action AI and strategy and mixed strategy profile this. We define this quantity called gain. Okay, I might just mangle the notation a little bit, but does not matter. AI, as long as I remain. Okay. This says you take basically, it's a mixed strategy profile. You define the gain function for X bar with respect to I and action AI like this. So now, can you relate this quantity gain with the Nash equilibria? Sorry, louder. Correct. All gains are zero means gain for every player I and every action AI is zero, right? That's literally invoking this. Okay. So then what we want to show is to show that this is true, right? What do we want to show? That there is such an X for which for every player and every action, the gain is zero. Okay. So now we define this quantity. Sorry, why? So I'm going to define this another probability distribution, which is a perturbed version of xi. Okay, for each player I, I'm going to define this. xi ai plus gain I ai mm, 1 plus ai prime yeah, I think everywhere. Okay. All right. So yi is a distribution for each of the action ai in the action space of the player I am dumping this much amount of probability mass. It's xi ai plus this gain value if the player shifts from x hat, xi, to this action ai, divided by 1 plus the summation of this. Okay. So I want to claim that y, so yi is basically a probability density function. Okay. So the denominator is quite predictable, as you can see. So if I sum over all the AIs, so what this means, that is, let me just write it. Yeah. yi AI is equal to 1. This would mean that yi is an element of the probability simplex of I. See this definition. Correct? Did you break it? I drop all the time, but correct? So this is this denominator, this perturbation is basically in the numerator. With this denominator basically allows us to do this. When I do a summation over all the AIs, you get a summation here, right? The summation also distributes over this gain quantity. xi is already a probability distribution. So summation of xi ai running over all the actions of in the action space of AI will already give you 1. What was the last thing you all heard?
So
I wrote
when
something
you
on the
start
board.
explaining the how the summation is equals to 1.
Okay, fine. That was literally the last thing I said with regards to this, right? Okay. So, okay. So this is the definition, okay? So what I'm not, okay. This, you can show, if you know these definitions, if you know that f is a continuous function, it just follows using the definition of continuity, okay? This space delta it's a subset of the Euclidean space, obviously. Delta is both convex and compact. So what does compact mean in this thing? In this, as a subset a space of the Euclidean space, compact basically means it is bounded and closed, right? Yeah. Okay. So this 3 things allows us to invoke, rather allowed Nash to invoke these results from topology known as fixed point theorem. Okay. So basically when you have these three things together, what you know is that we are using Brewer here, and there are several fixed point theorems in literature. The original proof used Kakutanes. It has a slightly different this thing, but Brewer's works just as well. Fixed point theorem says that there exists an X in the domain such that f of X is equal to X. Okay. All right. So I'm just going to Brewer's theorem. I'm just going to write for completeness. We basically are using let D be convex and compact of the Euclidean space. F is continuous. There exists X such that just whatever we said. It's exactly that. Okay, nothing more. So what we are going to do is, so any idea how we might use this fixed point result? We will show that such a fixed point, which we know exists, is basically a Nash equilibrium. Okay, so claim 2 is X is Nash equilibrium. Okay, just 5 minutes and I'm going to try to finish this. Okay, proof. Suppose not. Then what? If X is not a fixed point theorem, or is not a Nash equilibrium, then what? Use the definition of gain. There exists I, action AI, such that gain is greater than 0. Correct? Good. Then so then, okay, but we know this is a fixed point, right? So let's look, what does this look? So fixed point is saying, well, X itself is of this kind, right? X1, X2, Xn. And it's mapping it back to that, correct? So if I'm going to get back the exact same distribution, probability mass wise also they should be same. So the fixed point property implies what? That YIAI, right, should be, this thing should be what? XIAI, right? Now, you wanted to say something? Okay. Correct? Okay. So, but then, question is, what kind of AI are we talking about here? Is this AI in the support of X hat or not? Tell me, what do you think? Gain is positive, so if X is not a Nash equilibria, then there exists something that gives, then there exists an action that allows me to have a proper positive deviation, correct? But I don't know whether X is a Nash equilibria or not. So let's just look at this quantity, right? And let's say, if XIAI is actually 0, right? So what are we saying? So the right-hand side is 0. In the left-hand side, you have this quantity, which is 0. But this gain quantity is not 0, correct? Because of the definition. Yes or no? And in the denominator, you obviously have a 1 plus non-zero quantity because the same gain quantity contributes to the summation, correct? So you get a left-hand side, which is not equal to the right-hand side. But the fixed point theorem says they have to be the same, correct? So then this should mean that AI should definitely, So xi ai cannot be 0, right? So this just means that ai is in the support of x. Okay, all right. What's the next thing? Let's keep in mind we are trying to show that this is a Nash equilibrium. Now, what? Hmm. There's no action for which I can do better meaning. Okay, this talks about not Nash equilibria. Sorry? I'm yes. Okay. Suppose. So X is not a Nash equilibrium. Okay. So how do I use that? Yes. So I know that their AI does give me a positive gain, right? But the point is to show, but I mean, I'm trying to show that this is not a Nash equilibrium, correct? So I have to show a contradiction that there is no, the positive gain cannot exist, right? So one thing to note here is if xi ai is in the support, okay? If I go back to this quantity, this is ultimately what decides this quantity features in the gain, this thing, right? This is the second term here. Gain basically captures how much more can you get than this quantity, right? xi ai being in the support means this quantity, this part contributes non-zero. So this term does not vanish unless itself is at 0. Gain being greater than 0 means this quantity here. So while I'm doing a summation AI here, I'm talking about this AI, which gives me a positive gain. Okay, so don't like keep that in mind. So this means this quantity, and let me say star x xi ai times this one ui hat ai, sorry, ai. This is strictly more than xi ai u. Yes, simple thing, right? Just using the gain quantity. This is the whole. This is the left-hand side. So we are saying the left-hand side is equal to a summation which contains a quantity which is some factor times more than the left-hand side. Okay. So to make this equal, if all the summands here, all the terms that appear in the summation have this property, they have a positive gain. Okay. The right-hand side would be greater than the left-hand side, right? Now, even if some terms just disappear, if all the terms that remain, right, are all positive, then also the right-hand side would be greater than the left-hand side. Yes. So that means that there must be something in the right-hand side that brings down the value. So there must be some quantity, there must be some action ai prime such that this quantity, right, is less than that ui x hat. Yes or no? Okay, so there exists ai such that, so that also has to be in the support such that ui Can these people see this side of the board? If they can't see, they should have said before, no? Is less than ui x hat. But then it means ai prime for this player I contributes 0 to the gain, right? Gain with respect to a prime I is 0. Now, what can we say? So if it's not a Nash equilibria, there is something that gives me a positive gain. But this thing, this linear expression tells me there must be something that brings the value down. Otherwise, the right-hand side would be greater than the left-hand side. So now what? Are we done? Again, let's go back to the fact that we're using a fixed point property. So for this a prime I, when I apply here, this left-hand side should be equal to xi, ai prime, correct? Yes or no? So there the gain becomes 0. So where should I write? I really need some space. You guys wrote this thing down, right? Maybe I just so yi a prime I is equal to xi a prime I plus the gain, which is 0, divided by 1 plus this quantity, correct? So you have a positive support. You have a non-zero quantity here divided by this, right? So can this be equal to xi a prime I? This is 0, right? This is a non-zero quantity. Yes, but is this going to disappear? This is the gain quantity, right? Over all actions. Can this quantity disappear? Meaning, can it become all of them, if all of them are 0, right? But I know that for AI, gain is not 0. And okay, and this quantity never becomes negative. It is capped at 0. That's the other thing. There's no cancellations possible. If as long as you get one non-zero contribution, you know that this summation cannot be 0, right? So this is why you have a more than one. The denominator is greater than 1. The numerator is xi ai prime. So obviously this whole thing fixed point property, correct? Okay, so that proof. So that completes the proof of the Nash equilibrium. It's that simple. I mean, yes. I mean, simple does not mean easy because this itself. But you see, there is something like it didn't just things did not just appear from vacuum. This is a natural way of capturing what was the utility of the deviation, why anybody would even deviate. Firstly, we had that ingredient that if there's a deviation strategy, then there's a deviating action. If we have a deviating action, we can quantify what that positive gain is with respect to for every player and for every action in his action space. That's what gain was doing. Then this idea, can you give me a nice sort of what is actually happening here? This is basically saying I'm going to weigh all those actions which gives this player a positive deviation over this mixed strategy X that is going to be weighed up. You give it additional weight by the amount by which he gains. The denominator is just to make it a probability distribution, very standard trick. So main thing is to look at the numerator. It's the same thing, slightly weighed up by the amount of gain. Then, of course, using this topological result, that when you have a function like this between the product simplex, you basically get a fixed point. Now, just using the definition of the fixed point, you can basically get this thing back. Okay. Okay. So tomorrow I took 5 minutes extra. I think that's not bad by my standards. So that finishes what I wanted to do primarily today. So tomorrow we will meet an IMSC, right? 3:15. I should tell you next week on 20th, exactly at 10 o'clock, I have a talk somewhere else in a college in Chennai. So I can't come here on Wednesday next week, but I would like to teach a longer class on Thursday, next Thursday. Is that okay? Then you guys come to the IMSC class. Okay, so it's a late evening and so on. So we can take a break, have whatever. So I'll just like to teach a little longer. Okay, so one of the things I'll just end. Do you all have to have a class right now? Can I take 2 minutes? Okay, so one thing is that this tells us that a Nash equilibrium always exists. Okay, this result set forth sort of a mathematical enterprise that has led to huge amount of work, really influential work across, like this was proved in 1945. Okay, and it's a very tiny, small one-page paper, like the journal size is this much. It's just remarkable. And this definition and this solution, this idea revolutionized the study of what was back then mathematical economics and became sort of what we now understand game theory. Now, the question is, this thing, just because it exists, does not tell us how to compute it. Because these results, fixed point theorems, for the most part, in their full generality, are highly non-constructive. The proof of the fixed point theorem, this Brewer's fixed point theorem, is via, there are lots of different ways of proving it. One of the most famous, this sort of very cute and beautiful way of proving it is using Sperner's lemma. Sperner is a result from combinators. So this is like really remarkable, like 3 very different branches of mathematics, seemingly very different. They all sort of commingle. Okay, so Sperner can be shown to be implying Brewer, Brewer implies Sperner, Sperner implies Nash, Nash, the whole thing. It basically goes in circles. So either way, it's very non-constructive. So we don't really, this does not give us a recipe to compute Nash equilibrium. Okay, so people have studied dynamics like that. Like over several rounds, can people sort of learn, the players who are playing, can they learn Nash equilibrium? There are some results which shows that such a kind of convergence happens. Sometimes they show it's such a thing may not happen. Okay, that's one thing. Another thing you must notice, this is like different in, this sort of results are a bit different from the other kinds of more standard algorithmic results that we see. There are 2 aspects. Nash equilibria exists for the game. That's the property. Now the question is, can the game designer or the analyzer compute it? That's one question. The second question is, people who are playing the game, can they compute it? So Nash equilibria is this thing where it's a profile. I play a mixed strategy, you play a mixed strategy, you play, all together have to form a Nash equilibria.